equation at the border end, superposition principle, and kind of hinted at this idea that we're going to actually demonstrate today, that if you had an nth order linear differential equation, the homogeneous, we're going to start with that first, then to get all the solutions, you have to come up with n independent solutions. We call them linearly independent. And again, let's kind of remind ourselves what linear independence means. Okay, so you have a set of functions, and this can be not necessarily a differential equation, just in general. Suppose we have a set of n functions, f sub n of x. Okay. And I emphasized, and I showed by example how it was important that we talk about linear dependence. Not only do you have to consider the functions under consideration, but also the interval. And I gave you an example, I think f of x equals x and g of x equals absolute x, where the functions were linearly independent in any interval as long as you excluded the origin. But if you include the origin, then they're linearly independent. Okay? So you always have to remember that when you talk about functions being linearly independent or dependent, it's also a function of the interval on which you're at. Okay, so we consider an interval, say, for definiteness, x between a and b, a closed interval. Okay? And I'm not going to do this formally because we did it before, but basically, just to remind you, we do c1 f1 of x plus c2 f2 of x plus dot 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 plus cn fn of x. And we demand that that's identically 0 in the interval ab. Okay? I mean, it's like an identity. In other words, it doesn't depend upon the value of x. And I gave you some examples, things like if I had, say, x cubed, x squared, and 6x cubed minus 5x squared, those three functions, they'd be linearly dependent, because clearly the third function is 6 times the first minus 5 times the second. That's very obvious, okay? And then I think I threw up the last time some crazy thing with trig functions. Excuse me. And we saw there that because, if you recall some trig identity from high school, they were dependent. And that kind of suggests that it's not so easy using the definition, the fundamental definition, to say whether or not a set of functions is dependent or independent. So we want to come up with some analytical test, okay? The book just kind of throws it. I can easily derive it, so we're going to do that here. Now, it does require some knowledge of determinants and stuff like that. So if you haven't had linear algebra, don't worry about it. I'm not called you responsible for it, but many people have. So I want to show you where that test comes from, so-called Wronskian. And the great thing about that is you don't have to really think. It's mechanical almost. In other words, you calculate something called the Wronskians, a certain determinant, and you'll find out that if it's non-zero, they're linearly independent. Unfortunately, the converse is not true in general. But many times, what we're interested in the context of differential equations is establishing that a set of functions are linearly independent. So actually, the theorem that we have is sufficient for most cases. Okay, so here's the equation over here. Let's start with the following. Let's get a necessary condition for dependence. Let's assume that these functions, f1, f2, and f sub n of x, are dependent in the interval. Okay? So suppose f1 of x, f2 of x, down to the last one, I called it f sub n of x, are linearly dependent in the interval ab. Okay, what does that say in words? It means that this equation, c1 f1 of x plus c2 f2 of x, all the way down to cn fn of x, will vanish identically in ab. Not all c's are equal to 0. That was the definition of linear dependence. Because clearly, if you choose all the c's equal to 0, no matter what the functions are, it's obvious, it's trivial, 0 equals 0. The idea of being linearly dependent, that says that you can get a non-trivial linear combination going to 0. Okay? So suppose f1 is linearly dependent, then let's call that equation 1. Okay? Then equation 1 is true with not all c's equal to 0. Okay? So there's at least one c not equal to 0, usually a bunch of them. Okay? Now, what we're going to do is the following. Okay? Let's assume the functions are differentiable. Clearly, in the context of differential equations, they're going to be because they're going to be solving differential equations. So we have c1 f1 of x plus c2 f2 of x, dot, dot, dot. Now, the c and fn of x is identical to 0 in ab. Not all c's equal to 0. If that's the case, can I just differentiate that expression and say the same thing? So we have the first equation. I'll just write it again. C1 F1 of x plus C2 F2 of x plus dot 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 plus Cn Fn of x is identically 0, not all c is equal to 0. Let me differentiate that once. I get C1 F1 prime of x plus C2 F2 prime of x, where prime means a derivative, right? Plus C sub n Fn prime of x identically 0 for the same c's, obviously, right? Just quick differentiating with respect to
Quick
x.
question,
Yeah.
Professor. When that line just above what you just wrote is, then 1 is true with not all c's?
That's right, yeah. Not all c's are
Okay.
0. That's right. That's the definition of linear dependence, okay? So we have this is true, not all c's equal to 0. This equation is also true, not all c's equal to 0. So all I'm doing is differentiating. And then clearly I can go to the second derivative. Let's stop at the n minus first derivative, so I'll get a square matrix over here. And I need a notation, f super n minus 1 of x, so I can see. Right, say f1 super n minus 1. It doesn't mean take f1 of x and raise it to the power of n minus 1. It means differentiated n minus 1 times, okay? Plus c2. Now I have f2 of x differentiated n minus 1 times, right? Plus dot 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 plus c sub n fn of x differentiated n minus 1 times is identically 0. So all these equations hold for the same values of the c's, not all 0. Now again, if you didn't have linear algebra, the next thing I'm going to say may not make too much sense, but if you've had linear algebra, there's a famous result that says if you have a set of homogeneous equations and equations and unknowns, think of these as the unknowns, C1, C2, C sub n, and has a non-trivial solution. The only way that can happen is if the determinant of the coefficients goes to 0. Because otherwise, Kramer's rule would come into play, you just get the trivial solution. Okay, so you write this in matrix vector notation. Now you have a matrix, f1 of x, f2 of x, and the very last column I have f sub n of x, right? What do I have in the second row? The derivative of the functions. So you got f1 primed of x, f2 primed of x, right? Dot, 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 down to f sub n primed of x, okay? And then, of course, we've got in the third row, depending upon the value of n, I've got the second or third derivative, and I terminate at the n minus 1 derivative. I'm just copying really from above. This becomes dot, 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 f n minus 1 sub n of x. That times the c vector is equal to 0. For linear algebra, that's a set of n homogeneous equations and unknowns. The only way to get a non-trivial solution is if the determinant of that thing equals 0. Okay? Therefore, the following determinant has to go to 0. And we'll just summarize this and then we'll illustrate it. f1 of x, f2 of x, down to f sub n of x. And then the second row, you need the derivative of the first function, the derivative of the second function, then the derivative of the nth function, all the way down to the very last row, which would be f1 n minus first derivative, right? f2 n minus first derivative with respect to x. Finally, f sub n of x n minus first derivative with respect to x is equal to 0. This is called the Wronskian, if you look at the book, that's the term. Wronskian, the Wronskian determinant. Okay? So what we've shown is that if a set of functions are linearly dependent in an interval, then this determinant, called the Wronskian, has to go to 0 identically in the interval. Okay? So, a little logic here. Suppose I have a set of functions, I calculate the Wronskian, and I find that it's not equal to 0. Then I know that they're linearly independent, right? Because if they were dependent, we just showed that the Wronskian has to go to 0. Now, in general, the converse of this is not true. Okay, because the Wronskian goes to 0, it doesn't mean necessarily that the functions are linearly dependent. However, in the context of differential equations, it is. Once you assume that these f's are not just arbitrary functions, but are solutions of a homogeneous linear equation, then this is a necessary and sufficient condition for linear dependence. Like I said, most of the differential equations you come across, at least in mechanics, will be second order, and you can tell We know how to tell independence and dependence for second order equations very easily. Remember, we showed that two functions are dependent if and only if one's a multiple of the other. So you don't need this fancy Wronskian thing, okay? But sometimes you just look at the functions and you say, I'm not sure if they're dependent or not. And this is just a surefire test to tell you if they're dependent or independent, okay? So functionally dependent, linearly dependent, Wronskian must vanish, or as a corollary, therefore, if the Wronskian is not equal to 0, that will imply that the functions are linearly independent. And again, I don't hold you responsible for this, because I know people don't necessarily have linear algebra as a prerequisite for this course. Okay, but for those who did, it's just good to to know that. Okay. Let's see. Let me give you some examples. Okay. And again, I'll try to do it for both parties here. Those who know linear algebra, and then if you didn't know linear algebra, at least I'll give you some type of what should I say, heuristic argument as to why these functions are dependent or independent. Let's consider the following example, 3 functions I'll take. Suppose I have a set of functions, 1, e to the x, and e to the minus x. And let's consider that on the interval minus infinity less than x less than infinity. In other words, all real values of x on the whole real line. Question is, are those 3 functions linearly dependent or not? Okay? Let's kind of do it heuristically first without the Wronskian test, okay? Let's graph them, okay? Here's the first guy, right? This is your f1 of x, that's equal to 1, right? The second guy is e to the x. You all know what that does, right? It just goes like this. So that's your f2 of x, which is e to the x. And what about e to the minus x? Okay, that just decays this way and then goes like this, right? So there's the 3 functions. Certainly any 2, take 2 at a time, right? It's obvious that 1 and e to the x are what? Linearly independent, right? There's no way that 1 and e to the x are multiples of one another. Similarly for 1 and e to the minus x, okay? What about e to the x and e to the minus x? No, one graph looks like that, one graph looks like that. They're not dependent, okay? But then, rigorously speaking, maybe the set e to the x, e to the minus x, and 1 are dependent, okay? But I think you can see, at least, again, heuristically at least, that can't possibly be the case. How can you come up with a linear combination of this curve, and this curve that goes identically to 0 for all x, okay? So our intuition kind of tells us that these are linearly independent. Okay? That's as far as I can go, and I have to be careful to say it's heuristic. It's not totally rigorous because we only can tell about linear dependence or independence by inspection if there's 2 functions involved. Then we know one has to be a multiple of the other. When it comes to 3 or more, you just kind of may say, well, it kind of looks like that. But that's not good enough for a mathematical proof, right? Okay. But yeah, if you didn't have linear algebra, that's the most I would expect you to be able to say. Okay. Let's go calculate the Wronskian for this thing, and I'm going to show you that it comes out to be non-zero. Okay? And again, Wronskian non-zero, what we proved, is they're going to have to be linearly independent. And that kind of will rigorously verify our intuition. Okay? And the way people kind of write this, they'll put the Wronskian, and then they'll put the functions in there. 1, e to the x, e to the minus x. Right? Just follow the recipe. What's in the first row? The 3 functions, which would be 1 e to the x and e to the minus x, right? What's in the second row? You take the derivative of those functions. 1 differentiates to 0. The derivative of e to the x is e to the x. And be careful here it's minus e to the minus x, right? Okay? And then in this case, remember one term is always to be square. So since n is equal to 3, we only go up to the second derivative. So now we differentiate once more, and we get 0 again, we get e to the x, and now we have e to the minus x. Okay? So is that determined? Okay. Again, if you haven't taken linear algebra, what I'm going to do next won't make any sense. Okay, but if you have, when you have a determinant, you can expand by any row or any column. Okay? What you do is, to make things easy for yourself, expand by the row or column that has the most zeros in it. okay? I'm gonna expand this determinant by the first column. So I get 1 times the subdeterminant, which is, I knock out that row and that column. I get e to the x, e to the minus x, e to the x, e to the minus x. I just knock out the first row and the first column. I think I have a minus I screwed up here, sign. I'm not going to get e to the x minus e to the minus x, e to the x, e to the minus x. Okay. And now you just kind of do, you know how to determine that times that is 1 minus a minus 1, which is a plus 2. So since the Wronskian came out to be 2, which is obviously non-zero, those functions are going to be linearly independent for all values of x. So therefore we conclude that linearly independent set. And again, why this is so important is because what we're going to show shortly, and I've mentioned several times, if you have, for example, a second order differential equation, which is very common, linear homogeneous, okay, you're going to have to come up with 2 linearly independent solutions. So if someone says, oh, x squared is a solution, you say, well, so is 6x squared. Yes, that is, rigorously speaking, but x squared and 6x squared are dependent, right? You want to get 2 functions that are not dependent, and they'll show that to give you the total solution of the homogeneous equation. Okay. Yeah.
So if this were equal to 0, then it would be linear independent.
Okay. What happens basically is that, I said very carefully, is that, let me be careful about this. Okay, the converse of that thing is not necessarily true. But if these were solutions to a differential equation, that's the context we're going to use them in, then what you said is correct.
Okay.
It's a necessary and sufficient condition. Yeah. If this Wronskian came out to be 0, they'd be linearly dependent. Because we're not just going to just throw functions up and just say, oh, they're dependent or not. What's the context of the whole course? It's differential equations.
Yeah.
And it comes out that if your functions, your 3 functions here happen to be solution of a homogeneous linear equation, then that test is sufficient and necessary.
Okay.
Yeah, so it works both ways. Yeah.
So with that, where you do the matrix, you do just that the one row?
Oh, because,
one column?
did you have linear algebra?
No.
Okay, so then I don't expect you to fill. But basically what happens is that when you have a determinant, okay, when you of course linear algebra, you teach about determinants, and one thing is how do you get a number from a matrix, right? And the idea is you expand by a row or a column. And it would be, if you expand by the first row, you'd get more terms, but believe me, the end result would be 2. So
Okay.
expand by the